Hello everyone, this is part 2 of Carbocation chemistry. It's better if you watch the previous video, which is the introductory idea of carbocation, and for that you can click on the link appearing on the screen. And for all the previous topics, the corresponding playlist link you can find in the description box. So let's start. Carbocations, if we do the classification, here you can see total 3 parts are there. In the first part there is methyl, primary, secondary, tertiary, then allylic, benzylic, then vinyl and aryl. Now when it is the first one, here the classification is mainly based on the carbocation, that is the carbon carrying the positive charge. This carbon is attached to how many carbon, depending on that this classification is done. Now the next one, which is allylic and benzylic, here the carbocation, just beside this carbocation you can see in the alpha position there is CC double bond. And vinyl and aryl, this is completely different because now the positive charge is present on that carbon which is part of a double bond. Fine. So different types of classification we can do, but first we will focus on this, that is methyl, primary, secondary, tertiary, or you can say 1 degree, 2 degree and 3 degree. So this is based on the number of carbon groups bonded to the carbon which is actually carrying the positive charge, and based on that the simplest way we can express it, the first one is methyl, because here you can see the carbon which is carrying the positive charge, there is no other carbon present, that is no other carbon attached to it. So this is the simplest possibility and we call it methyl. Then primary, one of the hydrogen, now it is replaced with the R group, it is alkyl group. That means here you will have one CC bond and 2 CH bond like this. Similarly, if you replace another hydrogen with another R group, now we will have secondary or 2 degree. In this case I can write it like this. And then the last hydrogen which is left, that is also replaced by R. So these are the 4 possibilities. Fine. Now the next carbocation, okay, before that I will see some examples of 1 degree, 2 degree, 3 degree. Because the previous examples that you have seen, that is the general way of expression, but now you can see the actual examples. So these 3 pictures all are 1 degree because the carbon carrying the positive charge, that is attached to one carbon. If you are having trouble to choose whether it is 1 degree, 2 degree or 3 degree, it is always better if you draw the full structure like this. The more you will practice, then just you will have a look and you can easily predict whether it is 1 degree, 2 degree or 3 degree. Even you don't have to write the full picture. But if you are at initial stage, it is better if you write the full structure. Now you can see, you can easily identify how many CC bonds are there. It is only 1, so that is why it is example of 2 degree. Similarly, the second one, it is attached to 2 hydrogen, right hand side, and left hand side there is 1 CC bond. And the last one also, this carbon carrying the positive charge, it is attached to one carbon which is this one and 2 hydrogen atoms. Next 3 examples are for 2 degree. Here this carbon, I am writing this like, that is a full elaborate structure. If you draw, it will be like this. So here you can see 2 CC bond, 1 CH bond, so that is why it is 2 degree. Similarly, the second picture, this carbon is attached to 2 more carbon and only 1 hydrogen, and the third picture attached to 1 hydrogen and 2 carbon. Fine. Next we will see examples of 3 degree. So in this case there is no CH bond. I am talking about the C plus, carbon carrying the positive charge, it is attached to 3 carbon. If you draw the structure, it will be like this. And to satisfy valency there will be 3 hydrogen. But just focus on this middle carbon which is carrying the positive charge. Sorry, it is C. There is total 3 CC bond and no CH. So that is why it is 3 degree. The second one also total 3 CC bonds and this one. Now what about allylic and benzylic? So in case of allylic and benzylic, now with respect to the C plus, if you consider the alpha position, you will see there is CC double bond. Now if it is simple CC double bond, it will be allylic. If it is CC double bond of benzene ring, it will be benzylic. So for allylic, the definition you can say that when the positive charge is right next to a CC double bond, then it will be allylic. Now for allylic, if we write the general structure, so see C plus, it is attached to 2 R group, it may be any alkyl group, and then just beside this C plus there is CC double bond, you can say it is the alpha position with respect to C plus. But if the structure is like this, suppose CC double bond, then CH2, then C plus. Now it is not the example of allylic. Fine. So don't think this is correct. The CC double bond, it must be at the alpha position with respect to the C plus. So that is, it is a general allylic carbocation structure. But if you have all these R groups as hydrogen atom, that is the simplest possibility. Now you can call it allylic carbocation. Fine. So in this case, how you will understand whether it is allylic? You will be able to draw some resonance structures. So the resonance structure you will get is, now this carbon will carry the positive charge. There will be a newly generated CC double bond. But this type of resonance structure you will not be able to draw for this one. So that is why in this way you can understand whether it is allylic carbocation or not. And if the positive charge is right next to a benzene ring, now this is also actually next to a CC double bond, but here this CC double bond is part of benzene ring. So general benzylic carbocation structure, here we have C plus which is attached to a benzene ring in the left hand side and 2 R groups. But if you have all these R groups as H, the simplest example is benzyl carbocation. Here also resonance structure is possible, just like the previous examples we have seen. Now there will be a newly generated double bond, positive charge, then CC double bond. Some more resonance structures also you can draw for this one. So this is all about allylic and benzylic. Fine. Next, vinyl and aryl. So for vinylic, how we can say it, that is the definition. A vinylic carbocation is any disubstituted trivalent. Look at these terms, disubstitution. But it is trivalent, just like any other carbocation. But here the carbon which is carrying the positive charge, that is part of a double bond. And it is now sp hybridized and linear geometry. So if we look at this general way of representing this vinyl carbocation, it is like this, where the carbon which is carrying the positive charge, that is also a part of CC double bond, and it is disubstituted. Left hand side one substitution, right hand side one substitution. But there are total 3 bonds. So here we have 2 sigma bond and we have 1 pi bond. So this is pi bond, this is sigma, this is sigma. Okay. And if you have all these R as a H atom, hydrogen atom, then that is the simplest example. Now the name is vinyl carbocation. CH2 double bond CH plus. Now why it is sp hybridized? It is because now you have 1 pi bond and 2 sigma bond. If you have sp hybridization, now you will get total 2 sp. There will be 1 p which is not part of hybridization, and these 2 electrons are involved in sigma bond. This electron which is in pure p orbital, that is part of pi bond, and the p orbital which is vacant, obviously it is also not part of hybridization, so that will be the vacant p orbital. Okay, so in this way we can explain how it is sp hybridized and it is linear geometry. When it is this double bond is part of aryl group, that is benzene ring, now it will be aryl carbocation. So when the carbon bearing the positive charge is part of a benzene ring, that is positive charge is present directly on the benzene ring, then it will be termed as aryl carbocation. So general structure, if we represent aryl carbocation, here we have benzene ring and all the other 5 positions there is, and there may be any group. And if you have all these groups as H, all these are groups, then it will be phenyl carbocation. So in this way we can do the classification of carbocation in different ways. Fine. But remember, as all of that is, I am talking about particularly these 2 examples, they are actually highly unstable, because you know positive charge on carbon, it is already electron deficient, and then again it is sp hybridization. That means we know here 50% s character is present. It is also electron deficient. So there is no such stabilizing factor. So that is why vinylic and aryl carbocation, they are very unstable. So you will hardly see any example of this, but still we should know it. So that is why I have discussed it. But remember, these are unlikely to be formed as intermediate in any reaction. Compared to this, the previous one, that is allylic, where resonance is possible, that we have seen. Now this is really stable, and that is because of this resonance. Now how to understand stability, for that we will that I will discuss in the next video. Okay, so stay tuned, and the next video, that will be all about the stability, which is very important for exam point of view. Okay, so thank you for listening.